Okay, students, welcome to Easy BTech, your guide for BTech and beyond. In the today's lecture, we will discuss about common emitter configuration. In the previous session, we discussed about common base configuration. Now, today we will discuss how the common emitter configuration is obtained and how its input and output characteristics and graphs are drawn here. Okay, students, we'll start it. See, common emitter configuration. Common emitter configurations. In a common emitter configuration, emitter is common between input and output terminal. Input and output terminal. It means now it is a base, it is a collector, it is an emitter. Emitter is grounded. Common means grounded. This side is an input terminal and this side is an output terminal. This emitter is common between input and output. Now input side is base and output side is collector. Output side is collector. Output side is collector. Okay. Emitter is grounded. Emitter is grounded. Now if you draw this structure, now you can see this is BC107. This is an NPN transistor. This terminal is an emitter. This terminal is a base. This terminal is a collector. Now this current we will call as input current IB. This current we will call as IC. It is grounded. This voltage we will call as an VBE. To operate this emitter base junction in forward bias, can give a positive voltage. To operate this region in reverse bias, this voltage is a VCC. This is the common emitter configuration. Common emitter configuration diagram. We know that from two-port network, parameters, we will write V1 is equal to H11 I1 plus H12 V2. I2 is equal to H21 I1 plus H22 V2. Okay, this we will call as an I1. This is V1. It is I2. This is V2. We will write this expression as V1 means VBE. VBE is equal to HIE into IB plus HRE VCE. Next, IC is equal to HFE IB plus H0 T VCE. It is equation. Okay, remember H11 we will write as an HI. H12 in the previous lecture we have discussed this. H21 as HF, H22 as HR. If it is common base configuration B, common emitter means E, common collector means C. Okay. This parameters, common emitter configurations, are expressed by input output characteristics. Now, if you study the input characteristics, if you from the input characteristics, what is an analysis? PEB is equal to HIE IB plus HRE VCE. Okay, by keeping output voltage VCE constant, by keeping output voltage VCE constant, note down the value of VEB versus IB. Both are input side only. Input side. Means from this graph we will write VEB is a function of HIE into IB. We will write input impedance HIE is equal to VEB, change in VEB by change in IB. Input impedance of common emitter configuration. It is approximately 1.1 kilo ohm, this value. Okay, if you see this graph, clearly understand here. We can plot a graph between IB versus VEB, keeping this VCE constant. Okay. That is input graph is input current IB and output input voltage VEB. Input current IB, output voltage VEB, and IB due to smaller in size and less doped, the current through the base is in terms of microamperes. The magnitude of the current for the base current is microamperes. Keeping VCB constant. It is similar to that of PN junction diode. Similar to that of PN junction diode forward bias characteristics. Forward bias characteristics. May get the graph in this manner. Okay, this is VCE 1 volt, VCE 2 volts. This we will call as a cut-in voltage, that is VEB, that is cut-in voltage 0.7 for 0.7 volts for silicon, 0.3 volts, 0.3 volts for germanium. Okay, here it is nothing but output voltage VCE constant, graph between IB versus PEB. Both are related to input side. That is a function V1 is equal to function of I comma V2. V1 is equal to function of I1. V2 constant. From this we will got the input characteristics. Of the common emitter configuration. Similarly, output characteristics we can plot a graph between output voltage VCE and output current IC, keeping input current constant. That is, I2 is a function of I1 comma V2. Now we will write I2 is a function of V2, keeping I1 constant. That is, I2 means IC is equal to H naught T into VCE, keeping IB constant. Okay, if you see this graph IC, VCE, okay. This region is known as a saturation region. This region is known as cutoff region. This region is known as active region. This region is known as active region. This is the various IB values, like IB at 10 microamperes, IB at 25 microamperes, 75 microamperes, 100 microamperes. You can get this graph. Okay. Now what is a cutoff region? What you can obtain from this cutoff region? cutoff region. Okay. Now you can see the students. Cutoff region. Cutoff region means this is a cutoff region. The region of the graph, the region of the graph lies below IB 0. Now these all are 10 IB values. What is IB value? 10 microampere, 25, 75 or 100 microamperes. IB 0 means in this axis only. The region of the graph lies below IB, below or when or IB 0. This region is known as a cutoff region. In this cutoff region, you can clearly see, and VC is also 0 in this case. Now from this graph you can clearly understand the cutoff region, both the current IC and IB are in a zero state, zero current. And similarly we will discuss saturation region. Saturation region. Next, region of the graph which lies above the IB is equal to 0. Region of the graph which lies above IB is equal to 0 and VCE is equal to VCE sat. Always remember VCE sat 0.2 volts for silicon, VCE sat 0.1 volt for germanium. Okay, this is about a saturation region. Next, active region. Active region. This region of the graph, this region of the graph, just IB greater than 0 and VCE is greater than 0. Same we will write that region. In an act, the region of graph which lies above IB greater than 0 and VCE greater than 0. This region is nothing but an active region. It means you will get a constant current. Okay students, this is about a common emitter configurations. This is about a common emitter configuration. Okay, easy BTech, guide for BTech and beyond. Thank you.